All right, let's get started. So today we're going to continue on where we left off. It was an exciting morning with the power going out and the internet going down. Administrative, the reading is now updated, and please make sure you're keeping up with the reading. We're going to transition to the material listed in the reading. Project 1 will be out by about 9 or 10 p.m. tonight. It'll be due on the 16th of September, and as I had discussed before, it'll involve MATLAB programming, and we'll spend a bunch of time today doing more stuff in MATLAB using the so-called stick breaking construct, which is something you'll need to implement sampling for a game of your design that you'll be modeling in MATLAB. So again, it's only 5-6 pages, but you'll have to make sure you engage the material regularly. Okay, so where we last left off, we talked about learning the set language, and we talked about set operations in general. And I'm going to stay closer to the laptop until I get a Bluetooth microphone. We rely on the microphone on the laptop to do screencasts. I am posting the screencasts on YouTube so that you can use it as a study guide. Basically the voice and annotations, all this stuff in a video format. So we talked about the so-called set language, and we gave two examples. Not something is equal to nothing. And so this idea of set language is to try to develop an intuitive feel for what this stuff might mean. And when we left off last time, we said, well, what does something mean? When we looked at the first one, something means that anything that you observe can happen, and that's noted by our sample space omega. And the example we gave was for the event for rolling of a die. And so, of course, omega sub die is equal to the set 1, 2, 3, 4, 5, and 6. If that's what quote-unquote something is, then not something is nothing. So if you look at the Venn diagram associated with omega, well, we have the event 1, the event 2, the event 3, the event 4, event 5, and event 6. So if we have something, well, that corresponds to the entire sample space, everything that's possible, and so the complement of that would be the empty set, right? And so that's the same as nothing, if you will, the nothing event. And then we talked about this case, not everything, right? And so everything, if you're looking at what everything is the sample space, but not everything means that we're getting as close to everything as we can possibly get. And so if everything is 1, 2, 3, 4, 5, and 6, then for the die, omega die, which we said was 1, 2, 3, 4, 5, and 6, well, there is one way you can have not everything. You can exclude one of these elements, and it doesn't matter which element it is. You could choose to exclude the 1, you could choose to exclude the 2, and have 1, 3, 4, 5, 6. You could exclude the 3 only, 4 only, 5 only, or 6 only. So if you said not everything, you're excluding one of them in one of the 6 different ways you can exclude one element. And then if you took the complement of not everything, well, that's the opposite. So in this case, if we excluded the 1 and we took the complement of that, well, going back to the Venn diagram, we have the event 1, 2, 3, 4, 5, and 6. Well, if we excluded 1, okay, what we're left with are not everything would be 2, 3, 4, 5, and 6. If we took the complement of 2, 3, 4, 5, and 6, the shaded region, that's the same as that 1, which is the thing we excluded, right? And so if you excluded the 1, the complement of that would be 1. If you excluded the 2 for your not everything, the complement of that would be 2, and so forth. So the complement of not everything would be at least 1, because excluding 1 is the biggest way you can say not everything, because everything is everything, but not everything means you're excluding in the smallest way possible something from everything. Does that make sense? Any questions about this? So please do try these exercises yourself when you read through the book. Don't just passively read it. Get a pen and paper or stylus or what have you, and actually go over these things yourself. That's how you get more of this practice. Any questions? All right, so let's continue along, and we're going to look at some more definitions, and this is in the book. If you have some events that are disjoint, what does disjoint mean? Let me ask you, what does disjoint mean? Oh, it's right there, the definition, right? But intuitively, what does disjoint mean? Anyone want to put themselves out there, him or herself? No? If they share no common values, and you're Coleman? Okay, all right. So Coleman says they share no values. If you were going to draw this mutually exclusive idea in the Venn diagram, here we have our Venn diagram, and let's go back to the die example. So our events in our sample space omega, 1, 2, 3, 4, 5, and 6. Let's take two events. Let's take, let's take I was going to take the evens and the odds, but you have too much stuff crisscrossing. So let's just say 1 through 3 is one event, right? The die roll is less than 4, or the die roll is greater than 3, right? So let's call less than 4 is this event, and we're just going to label that A. That consists of outcomes 1, 2, and 3 on the die. And greater than 3, that consists of these 3 events, 4, 5, and 6. We're going to label that B. So you'll notice here, well, my bad drawing here, but in Venn diagram space, event A and event B do not overlap. They don't share any values, right? And so this idea of sharing values, if you visualize that in the Venn diagram, that means they are separate from one another, right? They don't overlap and they don't share values, okay? So that's what disjoint means. We could also draw another disjoint set for the Venn diagram for the die. 1, 2, 3, 4, 5, and 6. Of course, the evens and the odds, oops, forgot the 4, and the odds, can't really draw that. So let me draw this weird circle. And I'm doing that on purpose so that they won't overlap, but you get the point, all right? I'd have to write them out differently in Venn diagram to make it look nicer. But the evens and the odds don't share any values. They don't overlap in Venn diagram, right? So two events are disjoint if their intersection is empty. If you take the intersection between two things, that's the empty set. And the empty set, if you were to write that out mathematically, that's equal to open, close, curly brace with nothing in it. It's empty, right? The cardinality, let me ask you, what's the cardinality of the empty set? 0. It is 0. There's nothing in it. There's nothing to count. Okay, right. So two events, A and B, are mutually exclusive or pairwise disjoint if any two of these events are disjoint from one another. What that means is that if you have a set of events and all pairs of those set of events are mutually exclusive, meaning their intersection is empty set, they don't overlap in Venn diagram, then that's called mutually exclusive. That set of events is mutually exclusive. So let's take an example. Go into the Venn diagram again for the dice. You have the events 1, 2, 3, 4, 5, and 6 for the outcomes. And let's take the singleton events. So there's an event, let's call that event A1. A1, that's the event 1. We have another event for 2, another for 3, another for 4, another for 5, another for 6. Now, it is the case that for each of these singleton events, and when I say singleton, I mean that the event only has a single thing in it, the cardinality is 1. For each of those, you can see they don't overlap in Venn diagram. Moreover, if you take the intersection between these two sets, for each pair, it's empty set. So if we took the intersection between 1 and 2, that's empty set. 1 and 3, that's empty set. 2 and 3, that's empty set. 2 and 4, that's empty set. All pairs, if you take the intersection between them, it leads to or results in the empty set. So that's what a mutually exclusive set of events is. So in this particular case, the singleton events for the die roll are mutually exclusive because any possible pairs of events in the singleton die roll events among them, the intersection between them is always empty. Okay. Any questions about this? That makes sense? Okay. So let's take a look at this other definition. Events A, B, and C are exhaustive if their union equals the whole sample space. And there are many different ways you can do that. What equals sample space means that you can build up precisely this sample space omega from the union of that set of events, A, B, and C. So let's take an example from the die example. Here we have, and I'm going to write it out so it looks neater, 2, 4, and 6. It doesn't matter where they are in the Venn diagram. I'm just doing it to make it look nicer. Here's 1, 3, and 5. So we have the 6 basic events for the die roll, and let me group them together into 2 events. The first one I'll call event A, are the evens, and the second one I'll call B, are the odds. So if I were to take, in this particular case, the union of A union B, that's going to be exactly my sample space for a die roll, right? So to prove it to you, A would be 2, 4, 6, union with B, the odds, 1, 3, and 5. Well, that's exactly 1, 2, 3, 4, I'm running out of space, 5, and 6, which is exactly our omega die, right? Any questions about this? Make sense? So these 2 properties, mutually exclusive and collectively exhaustive, I'm going to add that modifier collectively, is a special property for a set of events that you see all over the place as it pertains to probability. It's a very useful thing. But before we can talk about mutually exclusive and collectively exhaustive, we have to define what each of those individual things means. Okay? Questions? All right. So let's take a look at rules of probability. And for this, we're going to go back to something we started at probably the second, I think it was 1A, module 1A. And we had this definition, and its purpose at the time was to show you how to read proofs. And we looked up this idea of what a sigma algebra is, and it said it was a set of subsets. And the biggest sigma algebra was the power set. And that power set was a set of all subsets for elements in our sample space omega. Okay. So now that we've built up a little bit of machinery about events, about set operations, about unions and things like that, let's revisit this statement, this proof. So we said that a collection M of events is a sigma algebra if the following 3 are true, these points A, B, and C. That means the entire sample space is in that sigma algebra. So we have our sigma algebra, script M, and script M is going to contain a set of things. Well, one of the things it has is the anything event, omega. So for a die roll, it would be omega die, is one of the things in this sigma algebra script M, right? Okay, so the next point, point B, says that every event in M, or sigma algebra, is contained along with its complement. So what that means is that if you have any event, and let's call that event E, also in this sigma algebra will be the complement of E. And it doesn't matter what that event is. Now, this third one says that if you have a finite, and we talked about what countable means, finite means it's countable. You can draw with one-to-one correspondence with the naturals, but it ends somewhere. So let's say you had an event or set 1, 2, 3, 4, 5, 6. Well, if that's my set or my event, and I have the natural numbers, and the natural numbers 1, 2, 3, 4, 5, 6, dot, 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 and it goes on. You draw a one-to-one correspondence between the set, can't get that, I'll just use black, and the naturals. So we pair these together, 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 and all of a sudden we run out of things in E. So we have some maximum. So that's what finite means, it ends, right? Countable means that you can put it in one-to-one correspondence with the naturals. So let's say if that event went on infinitely, but you can still pair it up with the naturals, that's called countable. So point C says that for every finite or countable collection of events, so that means you can have a set of events, and that's a complex event. So if you said, let my event be evens in the dice game, that would be 2, 4, 6. Is this finite or countable? Is it? Is it finite or countable? Can you count this set, E, the evens? Okay. How many items are in it? 3. How do you know it's 3? I know you can see it, but I'm trying to get you through the process. You can put it in one-to-one correspondence with the naturals, right? Now, the reason why I stress that, because absolutely you can eyeball this and say, oh yeah, of course, it's 3 things, I can see it. But I want you to practice using the process, because after these simple events, when we get to more complex events and schemes for how you enumerate the number of things in your complex event, you're not going to be able to eyeball it. So it's important to get into the practice of saying counting means putting in one-to-one correspondence with the naturals. Okay? All right. So there are 3. So for every finite or countable collection of events in our sigma algebra M, point C, contained along with its union, right? It's contained along with its union. So that means if you have a collection of events like 2, 4, 6, or 2 individually, 4 individually, the 4 outcome, 6 individually. Now if 2, 4, and 6 are in this thing we're calling our sigma algebra script M, so too are all the unions of this finite set of events. So that means if I said the evens are in your sigma algebra, you'd say, aha, by this definition of bullet point C, so too are 2 union 4, so 2, 4. So too are 2 union 6, 2, 6. So too are 4 union 6, 4, comma 6. Okay? So that's what that point means, and what it allows you to do, it says that if you have the singleton events, you also have all combinations of events comprised of the singleton. And that allows you the ability to construct these complex events. So that's what point C is saying. Any questions? Yes?
Is 2, 4, 6 included in that?
Yes, absolutely, because that's a union of these things. I forgot that, thank you. 2, 4, and 6, which is just the union of all 3 of this finite set of 3 things. Okay. Any other questions? Okay. So let's go forward. And we talked about these boundary value conditions, the quote-unquote degenerate sigma algebra, right? This is the simplest sigma algebra you can have. It's the sigma algebra script M that contains omega, and it contains omega's complement, right? So going back to that second definition, if an event is in M, or sigma algebra, its complement is in the sigma algebra. So if omega is in the sigma algebra, empty set is the same as the complement of the anything event, right? You could call omega something, and you could call omega bar nothing, okay? On the other extreme, the biggest, the richest, or the so-called densest sigma algebra is the one that has all possible subsets. So in case of the die roll, and I'm not going to write it out, that would be sigma algebra for the die roll. That would contain, well, it has to contain omega, has to contain the empty set. It would have the singletons, 1, 2, 3, 4, 5, and 6. It would contain the unions between 2, and I'm not going to do all of them, 1 union with 2, 1 union with 3, and so forth. It will contain the three-way unions. That would be 1 union with 2, union with 3. That would be 1 union with 2, union with 4, and so forth. It would contain the four-way unions. 1 union with 2, union with 3, union with 4. 1 union with 2, union with 3, union is 5, and so forth. It will contain the five-way union. 1 union with 2, union with 3, union with 4, union with 5. 1 union with 2 union with 3, union with 4, union with 5, union with 6. And of course, omega is already there, right? I'm not going to enumerate all of them, but you can imagine you could list them out, right? The power set is of cardinality 2 is of size 2 to the cardinality of the thing you're taking the power set over. All right, so it gets really big really quickly. And if you have this so-called dense sigma algebra, which has the power set of all the events you can draw on our sample space omega, that defines anything you could come up with for a coin if omega was omega die, right? Because you could say, I'm going to gamble on whether it's even. I'm going to gamble on whether it's odd. I'm going to gamble on whether it's less than 4. I'm going to gamble on whether it's less than 3 but greater than 5, right? Any possible outcome you could conceive of for a coin game, you can describe by this dense sigma algebra, okay? Don't believe me, try it yourself, right? Because you always will form some event from something from the full power set over these variables, okay? All right, any questions about that? All right. So we're going to make use of that in the project, and it's going to be for you to come up with a game, right? And I'm going to have some requirements for that game, but outside of those requirements, you're free to come up with any version of a game that you'd like, and you're going to be implementing that in MATLAB and answering a couple questions based on that. Okay? All right. No questions about this? Any questions? All right, so that should look a little bit more familiar now that we've revisited it after talking about events and such. All right, so let's take a look more formally at this idea of what a probability is. So we talked about this idea of when can I see you again, right? The frequency at which you can expect a particular event reoccur, when you'll see it again over a large number of trials or a large number of observations. Now, more formally, what a probability is, it's a function, right? And when you see this function notation, right, the name of the function is here, and the domain of the function, this is the domain, and that domain, each element of that domain is paired with something in the range, right? So here, a probability P, so it's going to be P of, probability of some event. The domain, meaning all the inputs over which you define your probabilities, are the sigma algebra, right? So if you had a probability of the evens, of the die coming up even, well, that particular parameter that you're using for your domain is going to be the event 2, 4, 6, right? If you're wondering about the probability of the outcome that the die is going to be a 3, that member of the domain is going to be the event 3. So that's why we have this whole machinery called sigma algebras, because we need to define the domain or the things over which we're computing our probabilities. Okay, so let's take a look at the range. Now the range are those things that are associated with the domain. And here, for probability, the range is the closed interval, so it includes the endpoint. So between 0 and 1, on the real number line. So here's 0 on the real number line. Here's 1. And we put these dots to mean that we're including the value 0 and 1 as well as everything between it. And this just happens to be a set of real numbers. Now, yes, I know we said that the set of real numbers is uncountably infinite. Absolutely, that doesn't change. But when we talk about probability, the probability, whatever that value is, it's always going to be a real number, and it's going to be in that interval, closed interval, between 0 and 1, right? So how I always pronounce it, how I learned it, it's in the closed interval between 0 and 1 on the real number line, and that connotes the fact that it's a real number. Okay. Any questions about this? Does that make sense? Yes? Okay. So there are some properties associated with probabilities. And one property, and these are pretty important, is called the unit measure, right? If you take the probability of the anything event, our omega, that's always equal to 1, right? So the probability of omega, if your input from your domain is omega, the resulting output, the range, is going to be 1, right? That means the probability of the anything event is always 1. If you were to look at it in terms of the Venn diagram, that would say the probability of any observable that you can see is going to be 1. Something is definitely going to happen, if you want to kind of make it more casual, right? Okay. Also, there's this thing called sigma additivity. And what it says is that if you have a countable collection of mutually exclusive events, that means they do not overlap in the Venn diagram, and let's call those events E1, E2, E3, and so forth. An example of that, again, going back to the dice, is the event 1, 2, 3, 4, 5, and 6. Now, instead of calling them 1, 2, 3, 4, 5, and 6, I could relabel them to be more general in terms of variables and call the first one event E1, the second one event E2, the third one event E3, then E4, the next one E5, and then lastly event E6, right? It doesn't matter what I call them. So when you see this notation, don't get hung up on the fact that sometimes you might use variables, sometimes you might use specific values, right? It's just a way of describing something. So if this is a finite or countable collection, so that means you can pair in one-to-one correspondence with the naturals and it ends, or if it doesn't end, countable, you can pair it in one-to-one correspondence with the naturals. Then, if you have the union of those events, right, the probability of that combined event is just the sum of the individual event probabilities. So what does that mean? So let's say I have E2, E3, E4, and E6. In that case, I have the 2 event, the 4 event, and the 6 event. If I wanted the probability of the union of E2, so that's the 2 event, union with the 4 event, union with the 6 event, what that says is that's the same as the sum of the probability of the 2 event, plus the probability of the 4 event, plus the probability of the 6 event, okay? So if I do that, well, that's just, well, the probability of the 2 event, that's 1/6. Probability of the 4 event, that's 1/6. Probability of the 6 event, that's 1/6. If I add up 1/6 plus 1/6 plus 1/6, that's equal to 3/6, which is the same as 1/2, right? And so what this says is that whenever you have a set of events, and the set of events is mutually exclusive, that means the intersection is empty, when you want the probability of the set you get when you combine them, right, that complex event, that probability of the complex event, provided the individual events are mutually exclusive, that probability of the combined event is just the sum of the individual probabilities, right? That's a useful property that we're going to need in order to calculate the probability of a more complex event beyond just a single observable. Okay? All right. Any questions about this? Does that make sense? Yes? No? Maybe? It's hot in here? Okay. I'm getting between you and lunch. Or maybe you already had lunch. All right. Anyways, I don't schedule the class meetings for some guys. Okay. So let's look at some nomenclature. We have our sample space omega. This contains all the possible observables that you can measure. It's also known as the anything event. You have its dual, the empty set. And let's do a little bit of manipulation. Well, if we said the probability of anything, of omega, is equal to 1, that's part of the definition of how a probability works and what a probability is. So we know that omega, if you intersect that with empty, that's empty, right? Something intersected with nothing is nothing. They don't share anything, right? So we know they're mutually exclusive. So let's try taking the probability of the union of them. So here, we have the probability of the union of something with nothing by our sigma additivity rule, right, our definition. That's just the sum of the individual probabilities. So that's probability of anything, which is 1, probability of empty, which is 0, right? So we know that result is 1. So how we can get the fact that when we want the probability of this empty set, what if we didn't know that, right? So what we would do would say the probability of omega plus, let me go down here so my penmanship is better, plus the probability of empty, we know that's equal to 1. Well, if this is 1, we subtract 1 from both sides, and we get probability of empty is equal to 0, right? So we can actually solve for that if we wanted to. It's just simple algebra, or just algebra. Okay. All right. Any questions about this? So we can actually use these properties to get at probabilities. And this just says, if you're going to solve a problem involving probabilities, and we'll see this with our modules on reliability, and if you do it one way and it's too hard, try looking for its complement and subtracting, right? And we'll talk more about that in the next module. So this also talks about this idea of how you construct complex events. If we have some event, which is the combination of singleton events, or smaller events, if you will, you can always find the probability of that complex event by adding, provided that these individual events, in this case omegas, are mutually exclusive, right? Their pairwise intersection is empty. That's a really important property, but you can use it to very easily, or more easily, calculate complex events. Okay, so let's use this in an example. Now, we've been talking about disjoint events. In this case, these things are not disjoint. We have two events, A and B, in the left-hand frame, and in the right-hand frame, we have three events, A, B, and C. Now, in this particular case, on the left, let's start with A union B. So we have A here, right? There's A. We have B. And you notice there's an intersection region here that's common to both A and B, right? That section you could label as A intersect B, right? So of course, this kind of breaks that additivity property. Because if you wanted the probability of A union B, well, A and B are not mutually exclusive. So you have to do something a little bit different. Likewise, if you want the probability of the complex event A union B union C, well, they overlap pairwise. A overlaps with B, A overlaps with C, B overlaps with C. And they also overlap three-way. And that's the intersect region A intersect B intersect C. So if you want the probability of the combination of these three events, you have to do some fixing. And let's talk about that in the next slide. So, probability of A union B, right? You have two events that overlap, and it's conceivable for some problem. You might want to take the probability of the complex event described by the union of those two events. So what do you do? Okay. Anyone want to guess? No? You subtract. Yes. minus of the overlap section. Okay. So Coleman says you subtract out this intersection part because, well, we'll show you. I'll show you in a moment. So naively, you might say, let me add the probability of A and the probability of B, right? Well, there's a problem there. And that problem is, and that's kind of partway there, but not completely correct. If we take A and B and we separate them out, we'll notice something here. That there's an intersect region that A shares commonly with B, and there's an intersect region that B shares commonly with A. And we're marking it here as A intersect B, right? So we've taken A and B, we kind of pull them apart, but we're just describing what those parts are. So if you add them together, the problem is, if you said probability of A, you're computing the probability of the entirety of A, including this region that's common with B, that also appears in B. And if you add to that the probability of B, you're including this common region in B a second time. So you end up double counting this intersect or this overlap region that they share in common. All right? Okay. So how you fix this up, and this is one case where there's a problem, the math broke. So the fix up is that you subtract out one of those copies. So here we have the probability of A. So that covers this entire region of A, including one copy of that intersect region. We add to that probability of B, so that includes this entire region, but that brings with it a copy of that intersect region, another copy. So now we have two copies of that. When you do the subtraction, you're getting rid of one of these copies of the intersect region. So imagine if somebody came along and took a bite and bit off that region. All you're left with is this kind of moon, looking, crescent moon looking version of B, what's left of B, and you're kind of fitting that to A's copy of the intersect region, right? So that's the proper way to do it. You're fixing up the fact that you're double counting that overlap region when you add the individual events, and it's double counted because they are not mutually exclusive, right? They do overlap. Does that make sense? Any questions? Okay. So let's take a look at frame B, the second frame here. We have three events for a three-way intersection. We have A, this big circle. We have B, this small circle. And we have C, this medium circle. So if we do this, we make an observation. You'll notice that there's a two-way intersection between A and C, right? So this is the two-way intersection between A and C. There's a two-way intersection between A and B. This is the two-way intersection between A and B. They overlap. Likewise for B and C, right? So let me redraw it. That's A, there's B, and there's C. A, B, and C. So let me not draw over it so you can see. So if we want the probability of the union of these three things, okay, well, we start out by adding the individual probabilities. When we do this, we're double counting the two-way intersection overlaps, and we're triple counting the three-way intersection, or the three-way overlap. And the three-way overlap is this section here, right? That's common to A, B, and C. So what do? We first add the individual probabilities, then we subtract out the two-way intersections. Now, of course, this two-way intersection, there's one intersection between A and B, there's another overlap region between A and C, and there's the overlap region between B and C. Okay, well, we did that, and that might seem fine, but there's a problem. When we did the subtraction of the two-way intersection, included in the two-way intersection is this region here that's common to all three. So we ended up getting rid of it in its entirety. So, oops, we broke it. We have to fix it back up, and how we do that is by adding that back in. All right? Now, there's something called the principle of inclusion-exclusion. There's a mechanized way you can actually do this for arbitrary overlaps between sets. And that won't be an assignment, but just making you aware that it's out there. Okay? All right. Any questions? That makes sense? So, yet again, this is an example of something breaking and someone developed a fix-up for it. Okay? All right. So we sum the probabilities, we fix up the doubly counted, and we add back in the thing that was subtracted 3 times where we took away the double counted ones. Okay. So we have an example of using some of this. Suppose we have a set A, and here's a Venn diagram, and now I'm just using symbols. And we have our omega sample space. It doesn't matter what it is. It could be die, it could be coin flip. And we have some subset of that we're calling event A. And we draw it in the Venn diagram. Everything that's outside of A is the complement of everything, all those events that are in event A, all those observations that are in event A. So we know from probability that the probability of the entire sample space, omega, is equal to 1. Okay. Here, we know that if we take the union between A and its complement, right, the probability that is equal to 1. But what if we didn't know that? How would you prove that? Well, we know that A and A bar are mutually exclusive. If we take A and we take its intersection with A bar, that's equal to the empty set, right? The intersection between any set and its complement is the empty set. If you're looking at it from the perspective of the Venn diagram, you see that A and A bar don't overlap. Now, when I draw this, you can think of A as being that circle, and then A bar is just that Venn diagram with that circle cut out of it. So imagine if you had a blue piece of paper and you cut a hole out of it in the position where A is, right? It just looks like you have a solid sheet of paper and you put the yellow on it, but that's not the case, right? Imagine cutting out this region, and that region is where A is, right? So you can see, in that case, they do not overlap in the Venn diagram, and therefore they are disjoint. So certainly they're mutually exclusive, and if you put them together by union, they're collectively exhaustive. If you fill in that hole again with that yellow circle, you get back your entire sample space omega, right? So you can create the sample space in its entirety from the union of A and A bar. Okay, so we know that A union with A bar is equal to our entire sample space, right? The first property, that's mutually exclusive, this one. The second property, that's the exhaustive property. So let's make use of this. Suppose we wanted the probability of A union with A bar. What if we didn't know what that was? Okay, well, we have the probability of A plus the probability of A bar. Well, we know that A union A bar is equal to omega. And we know we can substitute probability of A union A bar. We can just replace this with omega, and we have the probability of omega we know from the definition of probability is equal to 1. So in that case, we know that this must be equal to 1, right? Okay. From sigma additivity, that point about probabilities, we know that if A and A bar are mutually exclusive, we can expand this as the probability of A plus the probability of A bar. So we put those two together, and now we equate this expansion with the probability of omega. We equate that with 1. So now we have the probability of A plus the probability of A bar is equal to 1, right? So now you can use a little bit of algebra, and now you'll subtract from both sides of equality this expression. So we say minus P of A on that side, and we write minus P of A on the other side. What does that give us? Well, these cancel, and now we have probability of A bar is equal to 1 minus probability of A, right? So that gives us the rule of complement, okay? So if you want the probability of the complement of something, that's the same as 1 minus the probability of that event. It all comes from the base rules and definitions that define these probabilities. And that's going to be important when we get to reliability, and when we cover the next module, we'll see why. This is in the book, but I have to go over it here. Okay? All right. Any questions about this? Does that make sense? Yes? No? All right. Okay. Independence. Independence is another way of saying mutually exclusive. That means that one event does not influence another event. That's what this overlap also encodes in the Venn diagram. Here we have a bunch of events. We're just labeling generally E1 through En, little n, so there are n many of them, doesn't matter what n is. And they are mutually exclusive of one another, and therefore independent. They don't share any information. So it just so happens, if you want to take the probability of the intersection of independent or mutually exclusive events, that's equal to the product of the individual event probabilities. So if you wanted the probability that your die roll was a 1, intersect with a 2, intersect with a 3, and so forth, that would be equal to the probability of getting a 1 times the probability of getting a 2, and so forth. Okay? That's just a property, and that's going to be very useful when you want to compute the intersection between events that are known not to intersect or overlap with one another. Okay? All right. Questions? No? All right. So we'll end that module, and let's see, what time do we have? Okay, we're to 1:15. Let's bring up the next module, and I'll just go to the laptop to do this because I'm going to segue to MATLAB. Let's see. Keep. So do that. Stop mirror. Okay. So let me pull up the next module here, and I'm only gonna. Where is it? Oh, I see. There we go. Slideshow. Start. There we go. All right, so let's start the next module. So there's the reading assignment. There's going to be a project out due on Monday the 16th of this month. So please start it right away. Now, we talked about a bunch of things. Most importantly, we said an event needs a bunch of things, something that happens, and that's the experiment or the so-called trial. We also need an observation, right? You have to observe something. Right? In order to talk about observations, you need to make a measurement, and therefore you also need to list out what those possible measurements or observations could be. Now, in the simple case for like a die or a coin flip, it's very easy, but when we get to counting, we'll go over schemes for how you determine what these observations are for complex scenarios. And then you also need what we're calling when can I see you again. I'm not going to play the video today. There are certain issues related to YouTube. So I'm not going to play it today, but you need this idea of how often you can see or what proportion of the time these particular or each of those observations occur. What we've been calling when can I see you again. When are you going to see, or how frequently are you going to see the heads or the tails, right? You need all of these things in your system to describe what's happening when the outcome is not certain. So we covered a lot of stuff so far, and after this week, congratulations, that's 2 weeks of a 16-week semester, 14 weeks to go. We talked about sigma algebra, and it's that mathematical structure, if you will. It has a bunch of stuff in it, and that stuff has properties. We talked about the axioms of probability, what a probability is. We talked about events and when can I see you again. about evaluating and calculating probabilities. We talked about this mutually exclusive and collectively exhaustive property that was very important to us. We also talked about probabilities of combined sets of events, both when they're not overlapping for union and intersection, and when they are overlapping for union. We have to fix up by subtracting when it breaks. Okay, so we did a lot of stuff, and let's segue to MATLAB, continue on in our whirlwind tour, and I'm going to introduce something called the stick-breaking construction. And this stick-breaking construction is a method used for implementing sampling. Once you know your sample space omega, how do you produce these samples in a way that's consistent with the probabilities associated with these particular observations? Okay, so let's, why MATLAB? And I think originally I had intended this to be the very first, early in the first module, first lecture, or 1A or 1A. But MATLAB is an environment. As of late, MATLAB is trying to compete with Jupyter Notebooks, so they have something called MATLAB Live Scripts, which is fairly new. It just works, right? Open source software is great, but commercial software, people's livelihoods depend on it working, and it just works. And the reason why I chose MATLAB for stochastic and data analytics is because they take care of a lot of the low-level loose ends that you have to pay attention to, like reading files and parsing things that just aren't as important for this particular course. MATLAB brings you much closer to bringing to life the mathematics, the tools of mathematics that we need for this class, and without you having to worry about pointers and all that low-level stuff. And so we talked a little bit about vectors, and we'll talk about the other thing in MATLAB called a cell array. We talked a little bit about functions and conditionals, if statements, but today we'll focus more on loops, and I'll bring up MATLAB and walk you through the stick-breaking construction, along with some other things, useful things like plotting and histograms through this example. So let's, oh crap, I should have, all right, let me do this. I knew I should have gone back to the mirror. Minimize that. Let me do this. Screen mirror, Mac Pro, because I want to draw. Stop mirror. Nope, don't stop. Let's hide more. Go with Dropbox, DSU, class, stochastic. Lectures, I had the wrong one. All right. Three. There we go. Okay, so let me go here, and from current, there we go. All right, so stick breaking. So it's called stick breaking, and it's a very simple reason why. You can imagine you have some stick, right? And let me see if I can change this. There we go. Nope, wrong one. Suppose you have a stick. All right. Okay. You're going outside in the woods, you find a stick, and that stick has some length. And this is a mechanism that's used, it's a type of so-called Monte Carlo method, and it's used to produce samples that adhere to certain biases. When these biases or weights are the same, you get random sampling. When they're not the same, you get something that's biased sampling. So let's say you have this stick, and let's say this stick has 6 sections, and these sections are going to correspond to the sides of a die. So you have, that's 2, that's 1, 2, 3, 4, 5, 6. You take this stick and you break it, right? You break it in 6 locations, and each of the locations has an equal length, right? And let's say that length is 10 units, and that length is another 10 units, could be 10 centimeters, doesn't matter what that length is. And each section is the same length, that standard length 10. Okay. So now, given that the stick is broken into 6 equal pieces, each of length 10. Now, you're going to come along and say somebody blindfolds you, and my artwork is not that good, and there's a blindfold. You can't see. Okay. And you have this ball, and let's call it a random ball. You're going to throw this ball up in the air, and the ball is going to come down somewhere along the length of the stick. Now, because you're blindfolded, you can't prefer a particular location. Say, I'm going to get the ball exactly over there. The ball can end up anywhere on this stick. Now, because there's no preference, we could say that every location on the stick is equally preferable. It's random, right? And let's just now label these pieces of the stick. Label that one 1, that's 2, 3, 4, 5, and 6. So if your ball can land in any location on the stick, that means any one of these pieces will be the location where that ball lands. Now, if the ball lands, say, here, we'll say that you selected a 2. If the ball lands here, we'll say that you selected a 4, right? So that's the whole stick breaking construction, right? It can be very sophisticated, even though it looks simple. And we're going to model that in MATLAB, and this is the construct you're going to use for randomizing the selection of a finite number of observable outcomes. Does that make sense? Okay, so let's go ahead and let's do that. So let me now exit this. Keep. Let's see. Stop mirror. Okay. I just dropped this. I dropped this so many times. There we go. So let's bring up MATLAB. And I'm running 2019A, which is what it'll prompt you to download, because it always prompts you to download the most recent thing. So let me go to preferences and make sure I have a big enough font for it to be, 26. Okay, so everyone in the back can see that, right? Okay, so let's create a new script. And the difference between a script and a function is that a script is just a program. A function is a special program that you can call from others and have to have that function signature at the beginning. So let me start out by just saving this. And let's call it stick test 2019. Oh, I had a practice one. Stick test underscore 2019. Let me do that. All right. So what we're going to start out is we're going to create our stick, and that stick is going to be an array. And, ooh, you know what? Let me see. To be real fancy. Screen mirror. We're in 331. If I can put this on the other screen, 3358, 3358. Okay. What did it do? Stop mirror. There we go. Now we're cooking with gas. All right. Awesome. So why did this go small? Why did that do that? Um, 331. Why did that do that? Is that 3358? 3358. Let me make that bigger. Yes. 333. Nope, it's still there. Okay. Settings. Control solstice. What just happened? When I'm up. Cancel. All right, so I'll just direct you to this screen. I'm sorry about that. I don't know why this happened. So I am recording again. So this is MATLAB. We'll call it stick test. All right, so now we're going to define the stick. And that stick is going to contain all of the lengths of size 10 that into which we broke the stick, right? So I'm going to use an array to do that. So the first length for the first portion is 10. Then we have 10, 10, 10. That's 5 of them. 1, 2, 3, 4, 5. And 6 of them, 10. Okay. So I define my stick as just being a set of lengths. And those lengths are, in this particular case, of equal size. So now we want num breaks. And that's the number of breaks along the stick. And that's just length of the stick, right? Now, of course, if you didn't know what the command was or wanted to play with it, you can use the command window interactively to try things out. So if I said S is equal to 10, 10, 10, 10, 10, 10, right? And then I say L equals length of S, right? Print out L, it's of size 6, right? So you can use this command window to interactively try stuff. And the nice thing is you can scroll up and look at commands and copy and paste them once you know something works, right? Okay, so please use that interactively. So we have num breaks, and I'm gonna make the font a little bit smaller because it's gonna make it easier to fit more stuff on the screen. So I'm gonna make this 20-point font, okay. So we have our stick, we have a number of breaks in the length of the stick, and then the first thing we're gonna do is we're gonna define the low end of the stick break and the high end of the stick break. And what we're going to end up doing is moving these cursors, low and high, to point to the beginning of each break in the stick and the end of each break in the stick. Okay. So the first thing we're going to do is we're going to so-called normalize it, right? Here we have 6 positions. Each one is of length 10, and we want to make it on a 0 to 1 scale called normalizing. So we're going to say norm stick is equal to stick, right? And then we're going to divide that by the sum of everything in the stick. So what does that do? Sum is a function built into MATLAB, and it's going to compute the sum of everything in that list. You just give it the list name, the vector name, and it knows how to iterate through and sum everything. MATLAB is very, very good with vector and matrix operations. So then what it's going to do is going to take each element of stick and divide it by whatever that sum is, and it's going to give us a normalized version. So let's take a look at that. Display done, and I like to do a display done at the end because it gives me an executable statement on which I can put a breakpoint, right? So let's run that and take a look at a few things. So if I put my cursor over stick, it's a 1 row by 6 column or vector of doubles. Double is the default real number type. And each position has 10 in it, and it's actually showing you what the contents of that is. If I wanted to display that in my command window, I can just type the name of the variable, stick, and it shows me the contents of that. Likewise, you can see in my memory window, in my workspace, you'll see here on the right-hand side, every variable that you create, it'll show you what that looks like in memory, and even allows you, if you double-click on it, to bring it up, and you can change those values live while you're stopped or paused in the debugger. Okay? All right. So if we do that, num breaks is 6, and I can do that interactively by putting the cursor over. It shows me a tooltip with that. Or I can just type in the command window num breaks, and it shows me 6. If I look at num breaks here in the workspace in that memory, it shows you variable num breaks, its value is 6. Okay? So if we look at the normalized stick break, we'll notice that it computed 0.1667, which is 1/6, right, for each value. Okay. So you can repeatedly apply an operation to every position in a vector or matrix through MATLAB quite easily. You just pose the algebraic expression divided by sum, and it applies that for you. And then the return value is 1 for 1, the same size as that vector. Okay? Any questions? No? Okay. So we have that, and now let's define a loop. And for the loop, I'll say for I equals or gets 1 colon num breaks and end, right? And 2 things happen. First, you'll notice here, it put this collapsible graphic element next to the opening of this for block, right? Now, it matches up the beginning and end of a block, and it allows you to collapse them to make it more compact when you're looking at it, right? So here I have my for loop. There's my variable, and it's going to be assigned a value from 1 to num breaks. Now, in MATLAB, when you want to specify a list of integers or a list of values, you type the low value, colon, and then the high value. So if I said 1, comma 5, enter, it gives me 1, 2, 3, 4, 5. It's like a Python, I know they call it Python, like an expansion. I can't remember what they call it in Python. So here we're saying loop, the loop variable is I, and it's going to vary within this list, and that list starts at 1, and the default is to increment by 1, and it goes up to num breaks. Now, if I had done 1, colon, 2, colon, 10, that version of the list increment, or the list enumeration, says that instead of incrementing by 1, I'm going to increment by 2. So what this says is start at 1, end at 10, if you can, and increment by 2 each time. So if I hit enter, it starts at 1, 1 plus 2 is 3, 3 plus 2 is 5, 7, and 9, right? And so what I like to do for programmability, you don't have to, it's not incorrect to do it this way, but I like to, I've always trained myself mentally to put 1 colon 1 colon where the end is. And it's not incorrect to just say 1 colon num breaks, but I like to do this because it looks nicer. You know at all times what it's doing. So now, what I'm going to do, I'm going to define a variable called low, and it's going to equal 0. And I'm going to define a variable called high. It's also equal to 0. And what I'm going to do is I'm going to start out here, and I'm going to set what is it? Brain fart. Low, high equals low plus norm stick the ith position. So what is that doing? What that's doing is saying that the length along that stick corresponding to the low value of that interval along the stick is going to be at low, and high is going to be a little bit more. That little bit more is the length of that segment, right? So here, the first segment is 10 units long, then this next one is 10 units long, and so forth. So low is going to start out at 0, and then high is going to start at the next segment, which is 10 more, because that segment length is 10. So let's prove this and actually look at what it does. We'll say message equals sprintf, right? So you can have formatted strings. Low equals %d, %f, comma, high equals %f, floating point. Close the string, and so you have the format f is replaced by the variable values, and we're going to say low and high. Okay, so we're going to do that, and then we're going to display message. So what I'm going to do is I'm incrementing these variables low and high. Low is going to point to the low end of the stick, high is going to point to the high end of the stick, and we're just going to print out those values. Okay, so let's save this and let's run it and see what we get. Oops. Let me see. No, that's not right. Low equals high. Low equals high, and high equals low plus, yes, I'm missing something. Okay, let me stop. I forgot the initialization. So there we go. Let me clear. Oops. Clear. CLC. Clear clears memory, and CLC clears the display. So let me run that again. So we start out here. Low is 0. High is 1.667, right? On the normalized stick, if we look at norm stick, the values are each 1.667. That goes back to each length being a 1/6 of the total length for each region of the stick, right? So now, the next iteration, low is the beginning of the next segment, and high is 1.667 greater than that. And all of this adheres to these weights corresponding to each segment, okay? So we keep doing that, and we iterate all the way through until we get to the end, Okay, great. So the next thing I want to do, any questions about this? And I'll post this MATLAB on the Blackboard alongside the slides for the module for lecture 3. So the next thing I want to do is we want to do that blindfolding and tossing that ball so that it lands anywhere on this stick. So what I'm going to do is I'm going to call this function called random. And if you type help random, it tells you what it does, right? It gives you a random number between 0 and 1, right? Or is it rand? Help rand. There it is. A random number between 0 and 1 on the real number line. So if I type rand, give me a single number, it's between 0 and 1. If I type rand again, give me a single number, it's between 0 and 1. Now it's a different number between 0 and 1. So it's going to choose any real number between 0 and 1 and only give you a single one of them. That's what that one parameter means. So what I'm going to do is I'm going to define a value called coin, rcoin, random coin. And random coin is going to be some number between 0 and 1 randomly chosen, rand, only get a single one. And so what I'm going to do, that norm stick, I'm going to see which segment that coin falls in, bless you. Is it on the first segment, the second segment, the third segment? Is it between low and high for that particular segment of the stick? Make sense? Yes? No? Okay. So I take our coin, right? It's now some number between 0 and 1. And now I'm going to test if our coin is greater than or equal to the low value on the stick, and at the same time our coin is less than the high value on the stick, then I'm going to do something. That means that my random coin between 0 and 1 is now on that particular section of the stick that I've broken up. What I'm going to do is I'm going to remember which section it was. So let me add a new variable that I'm going to call selection, right? And I'm going to initialize it to -1 for various reasons I'll talk about another time. And I'm going to say in this if block, well, I'm going to set selection equals to I, which is that corresponding region of the stick. So we have 6 regions, so I could be either 1, 2, 3, 4, 5, or the 6th region, right? Okay, so now I'm going to print out what my selection is, and I'm going to say sprintf down here, message sprintf, and it's a formatted output. Selection equals, it's decimal, %d, selection. Okay, so I'm going to run this a couple times, quit debugging, save, and clear, CLC, and I'm going to run this a few times. So I start out, I create my stick. Ooh, we're till 1:15. Oh, crap. All right, let me end there, and we'll pick back up. I'm 2 minutes over. All right, we'll pick back up on Tuesday. All right.